Today we're covering section 5.1, which is on exponential functions, and we have to understand first of all what an exponential function is. An exponential function is defined for all real numbers, and the formula for that is f of x equals a to the x power. That's a base of a. The limitations are a has to be positive and a cannot be 1. So first of all, we want to evaluate the following things, and we're going to use our calculators for this, and so I will go through that on the calculator.
So as we look at example 1, on our calculators, what we're going to do is notice we've got 7 to the x power. We're given f of x, which means the x value is 2, so we are going to type in 7 raised to the second power, and we get 49 for a. Then going to b, the new x value is negative 2/3. Now you have to be a little bit careful here. We still go 7 raised to the, but when you have anything more than just one number in the exponent, we have to put parentheses around this. So we're going to take 7 raised to the parenthesis negative 2/3 power, and that's how we put negative 2/3 in the exponent, and that gives us this decimal, and then we would round that off to approximately 0.2733. In C, we've got an x value of pi, so we've got 7 raised to the pi button is second, and that same caret symbol. So that's 7 raised to the pi power, and you can see that's 451.808 approximately. And then the last one, part D, 7 raised to the square root of 2. The square root symbol is right here, diagonally up from the 7. And then we'll put in our 2, close parentheses, and we get 15.673 approximately.
Now, we want to draw f of x equals 2 to the x power. And to do that, we're just going to make a quick t-chart. If we think about these values, when we do exponential functions, we want to keep our values relatively close to 0. So let's go with negative 2, negative 1, 0, 1, 2, and 3. So if we plug in a 3, 2 to the third power is 8. If we plug in a 2, 2 squared is 4. When we plug in a 1, 2 to the first power is 2. 2 to the 0 power is 1. Now 2 to the negative first power, remember the negative exponent means the reciprocal, so it ends up being 1 over 2 to the first power, which is 1/2. Then 2 to the negative second is 1 over 2 squared, which is 1/4. So when we graph this, we have these values. We have 3, 8, 2, 4, 1, 2, 0, 1, negative 1, comma 1/2, and then 1/4. So if you think about what's going to happen here with this, that reciprocal is going to keep getting, the bottom number is going to keep doubling, and it's going to keep getting closer and closer to 0. On the right-hand side, the numbers are going to keep doubling as you go to the right. And so this thing is going to look like this. It's going to increase to the right, it's going to decrease to the left. Now let's take a look at another example. 1/3 to the x power. So once again, we're going to keep our values relatively close to 0. So negative 2, negative 1, 0, 1, and 2. And if we have 1/3 to the second power, 1/3 times 1/3 is 1/9. Then 1/3 to the first power is 1/3. 1/3 to the 0 power is 1. 1/3 to the negative first. Remember, the negative exponent makes the reciprocal, so it ends up being 3 over 1 to the first power, which is just 3. And then you can see the same thing happens here, 1/3 to the negative second becomes 3 over 1 to the second, and that's 9. So the graph of this one is going to look like this. -2, 9, -1, 3, 0, 1, 1, 1/3, 2, 1/9, and so we get this sort of a graph right here. Now the thing to understand here is when that base is bigger than 1, anytime b is greater than 1, it's going to look something like this graph. It's going to be increasing as it goes from left to right. But when the base is between 0 and 1, you're multiplying by a fraction over and over and over again. It's going to make that graph, or the function, decrease as you go to the right. There's a little nicer picture of f of x equals 2 to the x, and then a little nicer picture of 1/3 to the x power. So the exponential function, f of x equals a to the x, again, a has to be greater than 0 and can't be equal to 1. If you think about it, it has a domain of all real numbers. We can take 2 and raise it to any power. But it has a range of only positive numbers from 0 to infinity. The graph of f has one of these shapes, and that's what we were just talking about. If a is greater than 1, I guess I used a instead of b. But if a is greater than 1, if the base is greater than 1, it's going to increase from left to right. And if the base is between 0 and 1, then it's going to decrease from left to right. For example 3, we want to find the graph of f of x equals a to the x given below. So the key thing is we know, you can ignore that b there, but we know that y will equal a to the x power. Well, the nice thing is they give us this ordered pair right here. That's one of the points on the graph of the line, so it makes this equation true. So the y value there is 3. We don't know what a is yet, but we know the x value is 1. So if we're figuring this out, we know that then a equals 3, and so our equation must be f of x equals 3 to the x power. So the problem is as easy as that when we have an ordered pair. We just plug it in and we solve for the base. Now looking at this one, we've got a different ordered pair given to us. So once again, we've got y equals a to the x power, but this time our y value is 2 and our x value is -1. Now remember what the -1 does. It makes it 1 over a to the first power. So if 2 equals the reciprocal of a, hopefully we can reason that 1/2 would equal a. To do it algebraically, we multiply by a on both sides, and then you'd have 2a equals 1, and then you divide by 2. You get the same answer. So then our equation is f of x equals 1/2 raised to the x power. So we want to use the graph of y equals 2 to the x power to help us sketch these three functions. Again, think about your transformations that we've learned in the past. What happens on a? Well, the part that makes it different is this part. -2 is added to the parent function. So what happens when you add -2? The function moves down. So unfortunately, I can't get the whole thing on my graph here. But this point right here will move down to -1, so we'll put it down there. This point will move down to 0, 2 units down. This point will move down from there, and every point will move 2 units down. Also the asymptote, well, let's draw this. It's going to come up through there. Also the asymptote, which was y equals 0, will move down also. So the new asymptote, even though you can't see it on the graph, will be y equals -2 because the asymptote will also move down 2 units. Okay, so there's a picture of that. You can see how the asymptote has moved down, and we get our graph there. So back to the parent function. Now what happens on b? We have -1/2 times 2 to the x power. So the negative, if you remember, reflects this function, so it's going to be going down. And then the 1/2 makes everything half as far from 0. So let's deal with the 1/2 first. So instead of this point being 1 unit away, it's now going to be a ½ unit away. Instead of this point being 2 units away from the x-axis, it's going to be 1 unit away. Instead of this one being 4 units away, it will now be 2 units away. So what's going to happen is, every one of these points is half as far. You're going to get this sort of a shape that goes up like that. It is going to increase more gradually because everything is only half as far from the x-axis. Then the other thing that happens is we reflect this over the x-axis. So this point will move down here, this point will move down here, this one will move down here, and now we're off the screen, but that one will go to -1 and then -2, etc. And here's what our graph is going to look like after we reflect it. It's going to be a more gradual curve. Notice the horizontal asymptote has not moved. It's still at 0. The stretching and reflecting doesn't change that, but we get that reflected graph there. Once again, back to the original one, and this one has k of x equals 2 to the x plus 3 power. Now here we're affecting the x, and remember, affecting the x moves left and right, and it always works the opposite of what you think. So if we're adding 3 to x, that's actually going to move it 3 units to the left. So this point moves to here, this point moves to here, this point moves to here, and you can see the whole graph gets shifted. Whoops, I missed that dot. But anyway, the whole graph gets shifted 3 units to the right. Same shape, just moved over. Horizontal asymptote, it doesn't move. Shifting it to the left, or I'm sorry, we're shifting the whole graph 3 units to the left. Shifting it to the left is not going to change the horizontal asymptote at all. So that horizontal asymptote will still be at y equals 0. Now there's one other type of base, a special base that we want to look at, and that's the natural base. Natural exponential function is the exponential function f of x equals e to the x power. In other words, it has a base of e. This is often referred to as the exponential function because it gets used a lot with that base of e. So we want to evaluate the following, and to do this, again, we'll use our calculators, and I'll show you exactly where that e key is on your calculator.
Looking at example 6, you can see the answers there, but again, here's how we do that. The base of e is a special base, and so it has a special button. It's second, and then this ln button right next to the 4. That gives us the e raised to a power, and we just want to type in 5 and close our parentheses. And we get, when we round it off to 4 decimal places, you can see our answer there. Then for b, we've got 3, and then again second, ln, and then we're going to type in -0.54. Close your parentheses, and we get an answer of 1.7482 as you look at that and round it off. And the last one, C, again second, ln, 3.2, close your parentheses, and we get that answer there.
Okay, we're going to describe these translations. Describe how the following would be sketched if we were given the graph of y equals e to the x power. Well, if we think about it, the negative right here, it's a reflection because it's a negative, but notice it's affecting the x, so it's moving things left and right. So this is a reflection over the y-axis. That's what that negative does. That's the only thing that has changed. The second one, part B, notice there's a couple things that happen. We've got a 3 here and a 0.5 here. So let's deal with the 0.5 first. It's in the exponent. The 0.5 is going to be a horizontal, again, it's affecting the x. It's a horizontal stretch. And if you remember, it always works the opposite of what you think. So you would think it's a shrink half as far, but it's actually a stretch 2 times as far from the y-axis. Now the 3, that is a vertical stretch. And that one does work the way we would think. So it's 3 times as far from the x-axis. So then we want to get a little picture of this, so it's going to go over my writing a little bit here. But to look at that, you can see there is the original one. It is a reflection. The original one would have looked like this. Okay? So the reflection is just over the y-axis, just like we mentioned. Then with this one, notice that, again, if you view this one as the original, this one has been stretched up, so the point would have been here at 1, but it got stretched up 3 times as far. It also got stretched horizontally, so this point that's at 2 normally would have been right here over that far, at -1. But it's been stretched vertically and horizontally, so that makes it a little bit tricky if you were going to graph this by hand. But we can describe it pretty easily. Okay, an infectious disease begins to spread in a small city of population 10,000. After T days, the number of persons who have succumbed to the virus is modeled by this function. And you can see the function there. How many people are there initially, or how many infected people are there initially when T is 0? Okay, well this one is actually pretty easy to do even without a calculator. What we have is 10,000 over 5 plus 1,245 e to the negative 0.97 times 0 power. Well, when you multiply something by 0, you get 0, and anything raised to the 0 power gives you 1. So what we have now is 10,000 divided by 1250. And so when we do that division on our calculator, or we reduce, or whatever, we end up with 8. There were 8 people who were infected initially.
So looking at part B, we want to put in these values 1 day, 2 days, and 5 days. So we're going to type in our function 10,000 divided by, and you have to put parentheses around this whole denominator for it to work right. So parentheses 5 plus 1,245 times e, second ln, raised to the negative 0.97 times 1 power. And then I need to close my parentheses there. Once for the exponent, once for the denominator, and when we hit enter, we get an answer of 20.966. So in this case, people infected, that's going to round off to 21. Now a nice feature of these calculators is, so that I don't have to retype that whole thing, I can use the second enter button and it will retype that whole thing for me, and all I have to do then is go back and change the x value, or the t value in this case, to a 2. And hit enter, and we get 54 when we round that off. I can do the same thing for 5 days, second enter, go back and change that 2 to a 5, and we get 678 people. Now the last thing we're supposed to do here is graph the function, so we'll go y equals, and we'll type this in, 10,000 divided by, parentheses, 5 plus 1,245, second natural log, negative 0.97, and our variable is x that we can use, and then we close our parentheses twice. Now when we click graph on this right away, notice we don't see anything. At least not very much. We see a little tiny curve right here. But you have to think about the situation here. In our situation, we're not going back in time, so we're going to start with 0 for the minimum x value. And then we see after 5 days there's 678. Let's go all the way to 50 days and see what happens there. The x scale, that just tells you how often there will be a hash, and I'll put that every 5. Then for our y minimum, obviously negative people can't be sick, so 0 to, we know there are 10,000 people in the town, and let's just say maybe 5,000 of them get sick as a maximum, and let's go by 500s for our y scale. So now when we graph this, hopefully we'll see something a little bit better. Okay, so now we're seeing that it's definitely leveling off, and since this was 5,000, maybe at, let's change our window one more time, and let's go down here, a y maximum of 2,500. Okay, so we can see it rises very quickly and then it levels off. For whatever reason, could be treatment or people are starting to stay inside or something. But that gives us a picture of that graph. If you look at this, it ends up leveling off right around, if we trace this, you can see right around 2,000. As we go through there, we're getting 2,000 for our, what we would call the horizontal asymptote.
The last topic we need to cover when we deal with exponentials is compound interest. And compound interest is calculated with this formula. That's something you're probably going to want to write down on your note sheet. I believe it's on there. But things that we have to worry about are the A of t is the amount after t years. P stands for the principal, which is the original amount or the initial amount. R is the interest rate per year, and that has to be written as a decimal. N is the number of times the interest is compounded per year, and then T is the number of years. So that formula, it's going to be important for us to know what those things stand for. So let's do example 9 here. This is again one we'll have to do on the graphing calculator, but we'll take a look at it. A sum of $1,000 is invested at an interest rate of 12% per year. Find the amounts in the account after 3 years if the interest is compounded annually. And so what we'll do is we'll set up the formulas, and then I'll use the calculator to actually solve them. So annually, we've got A of 3 will equal, whoops, I need my principal in there. A of 3 will equal 1,000 times 1 plus R, and the R value here is 12%, so 0.12 divided by N, and since this is annually, N would just be 1, to the NT power, so 1, and then the time is 3. So that will be our formula for annual. Then semi-annual. The formula will change in that N will now equal 2. So A of 3 will equal 1,000. 1 plus 0.12 over 2 to the 2 times 3 power. So all we're doing is we're changing how many times per year the interest is compounded. Then if we go quarterly, we've got A of 3 equals 1,000. 1 plus 0.12 over quarterly means it is compounded 4 times per year, once every quarter. And so N is 4 in both of those spots. Then if we look at monthly, A of 3 equals 1,000. 1 plus 0.12 over 12. Monthly is 12 times per year, and then we put in a 12 for both of those N's. And then finally, daily, A of 3 equals 1,000. 1 plus 0.12 daily. There are 365 days in a year, so it's compounded that many times.
So we've set up these problems, and you don't see it up there anymore, but if you remember, we set up the problems, and the first one was 1,000 times 1 plus 0.12 divided by 1, close your parentheses, raised to the parentheses 1 times 3 power. And you can see that we round this off to the nearest cent. That would be $1,404.93. Now to use that same little trick we used earlier, second enter. For semi-annually, those n values will change to 2s, so I will change that 1 to a 2 and this 1 to a 2. And notice now we get $1,418.52 when we round that off. Second enter again. Quarterly is 4 times per year, so we're going to change these 2s to 4s now. And we get 1,425.76. Again, 76 cents there. Then, when we do monthly, again, second enter will put that in for us, but notice this time I can't just replace the 4 because I can put in the 1 and it's going to type over this. So I have to do second delete, and that's the insert key, and then I can put my 2 in there. Same thing for this one. Second insert, I'll put my 2 in. And notice our answer here is $1,430.77, so about $5 more if you compound it monthly. And then the last one is daily. And again, second enter, and we're going to go in here. And daily, there's 365 days, so 3, 6. Second delete so that we can insert that 5. Same thing down here on the bottom, 3, 6. We need to insert the 5. And when we hit enter there, we see $1,433.24.
Now notice the value keeps going up the more times we compound it, but it doesn't go up super dramatically. It's going to go up a little bit at a time as we look at these, but we'll type them into the calculator again and make sure we understand how to type that in. Finally, interest compounded continuously. This is, again, a base of E coming into play. Continuously compounded interest is calculated by this formula. And a lot of times people call this the PERT formula. And notice all the variables stand for the same thing. A of t is still the amount after t years. P is still the principal. R is still the interest rate as a decimal. And then t is the number of years. So we're going to do this same problem now using the continuously compounded formula. And so we would have A of 3 equals 1,000, the principal, times E this time to the 0.12 times 3 power. And again, I will calculate that for you on the calculator so that you see exactly how that needs to be typed in.
I'm going to leave that $1,433.24 on there just for comparison. Now using the PERT formula, we have 1,000. Second ln gives us the E. Our rate is 12% times our time, which is 3 years. And notice what we get here, $1,433.33. So just 9 more cents by compounding continuously as opposed to daily. So you can see the differences there. 12%, a pretty high interest rate. $1,000, a pretty low amount of money for an investment.
Section 5.1, and you can see that and go ahead and get started on that. And if you you'll have time tomorrow to work on that in class, so go ahead and get started on that.